we'll come to that. All right, let's say we didn't stuff anything in there. How much charge, is there any limit to the charge you can put on these plates? What would be the limiting factor? I'm sorry?
3 million volts per
Yeah,
meter.
this electric field cannot exceed 3 million volt per meter. Okay, if that electric field exceeded there, then this becomes, the air becomes conducting and they will neutralize. All the energy will go down the drain. Okay, so if you put a piece of rubber, it turns out that that electric field, the charge on this capacitor can be increased because lightning in rubber and dielectrics happen at higher fields, so you can charge the capacitor even more. So you can store more energy in the capacitors. Okay, so anyway, and so we'll talk about all of that. Okay, so let me show you a capacitor first. We've seen these guys before. All right. So in a static situation, electric fields in a metal are zero. Okay, but when you connect a battery to a piece of metal, what the battery can do is it'll establish an electric field in a metal. Okay, so in dynamic situations, you can have non-zero electric fields in a metal. And when you have an electric field in a metal, what is the metal? It has a bunch of free charges. So those charges will respond to the electric field. Okay. So when I turn on the battery, it'll establish an electric field like that. Electric field will point like this and go like this. And of course, electrons will flow opposite to the electric field, and electrons will flow there. Okay? So whenever there's charge flowing, that means there's an electric field there. Okay, so in dynamic situations, you can establish electric fields. All right, so, and all this will happen super fast. Okay. So you blinked and it all happened. Okay, so what happened when you connected the battery? It established an electric field like this. Electrons flowed from here to there, and these electrons repelled electrons from on this plate, and those guys flowed over here. So if this was a 1.5 volt battery, electrons flowed into the capacitor till the potential difference between these guys became 1.5 volts. And then at that point, the electric field here went to zero and the flow of charges stopped. Okay. And from an energy perspective, all you did was you transferred energy from this device to that device. And again, like we said, why do we do this? Because this device can release the stored energy very fast, okay, extremely fast. So for instance, if your goal was to light up a flashlight, okay, a flash camera, you did that, and for this guy to light up like 200 100-watt bulbs, you had to release that energy very fast. And that guy lit up like 200 100-watt bulbs for about a millisecond. Okay. And that's what you did. Okay, capacitors are used to tune receivers. What is this? What does that mean? Do you guys know? Do you use any of these guys? Your life couldn't work without it. Every wireless device is a receiver for electromagnetic waves. So how does this guy pick up signals? Okay, here's the basic circuit. So this is the electrical symbol for a capacitor. This is the electrical symbol for an inductor. Okay. Now all right, so let's, before we go any further, so let me go back and okay, so how long will this oscillate? Forever. So as long as the damping is zero, this will oscillate forever. You have a system that will oscillate. When will a system oscillate? Why does a system oscillate? For a system to oscillate, you need at least two kinds of energy. And all that is happening is energy is going from one bin to another. This happens to have three kinds of energy. It has spring potential energy, gravitational potential energy, and kinetic energy. Okay, so all that is happening is, and see, the total energy remains constant as long as there's no damping, no friction, and energy is being transferred from one bin to another. Here there happens to be three bins. So for an oscillatory system, for you to have an oscillatory system, you have to have several bins of energy. This guy is an electrical equivalent of it. Okay. Damping here would be, resistance would be, friction would be provided by resistance. So here's an ideal situation. I'm not drawn resistance. Okay. This fella stores energy in electric fields. This fella stores energy in magnetic fields. And we'll talk about that. This is an inductor. We'll talk about that in a couple of chapters. So if you charge this guy and let go, this will oscillate. Current will go like that, back and forth like this. And it'll oscillate forever. Okay, if no damping is present. And it has a frequency. Frequency of oscillation depends on these values. Okay, so this is, and again, you will learn all of this. L is the value of the inductance. Omega equal to 2 pi f equal to 1 over square root of LC. Okay, so that is the frequency of oscillation. Okay, now remind me of resonance. What does resonance mean?
Resonance is basically the driving force that you put on it to make that puts it in line with the material or whatever you have. So like you push when it would push and you pull when it would pull to intensify it.
Yeah, so if you have a system which has a natural frequency of oscillation, and if you have a driver that is driving at its natural frequency, then you can set up large amplitude oscillations. Okay. All right, so let's say this guy has a frequency, its natural frequency is 100 megahertz. FM radio is megahertz. Okay. Now let's say in this room, there's a signal of 99 megahertz, 100 megahertz, 101 megahertz. There are many more. There's about 30 frequencies trying to get your attention here. Okay, so this frequency and the natural frequency of this guy is 100 megahertz. This frequency will set up oscillations here, but the amplitude will be small. You guys remember that experiment we did with the strings? This guy will also set up currents here, and he'll set up the largest currents. And this guy will also set up currents. Okay? So this guy, whose frequency matches the frequency of this guy, will set up the largest current. Okay? And how do you pick up this signal? What you do is you stick two rabbit ears up. You stick antennas on this capacitor and pick up the signal. Okay? And all these circuits have a variable inductor or a variable capacitor. And that is the tuning part. Okay? So you tune the frequency of the circuit to match the frequency you want to try and pick up. You know? And you know, there's trillions and trillions of copies of this basic circuit in the world today. Because this is how every wireless device is talking to each other. Okay. My iPad is wirelessly talking to a device there. Yeah. All right, so that's what we mean by the capacitors are used to tune receivers as filters and power supplies and energy and charge storing devices, among other things. Okay. So capacitors store electrical energy just like batteries, except that they can discharge their energy much faster, billions of times faster. Okay. Here's a circuit that you're all familiar with. Okay. Energy stored in capacitors is used to light flash bulbs. So in a flash bulb camera, you store about 20 joules of energy. Okay, so we saw where did my flash bulb go? Okay, so when you charge the capacitor, you've stored about 20 joules of energy here, and then you discharge this energy to the flash bulb, through the flash bulb. And what did this flash bulb do? It'll turn this room that is in pitch blackness to daylight for a millisecond. And then you can take your picture. Okay. All right, see, 20 joules is 20 kilowatts. 20 kilowatts for a millisecond. The milli kills that, and watt per second is a joule. And here's 20 kilowatts, 1,000 watts times 1 millisecond. This is 200 into 100 watts, 1 millisecond. So that's what you can do. With 20 joules, you can light up 200 100-watt bulbs for a millisecond. Okay. And that's what your flash bulb does. Okay. And if you want, with 20 joules, your weight, so mgh, your weight is about 100 kgs times 1,000, G is 10, so that's 1,000.05. .05. 100, no, 0.02. So you can jump 1 inch with 20 joules. All right. David can jump 2 inches because he's only 50 kgs. All right, so capacitors are any two pieces of metal. Okay? And when you charge them, you've stored energy in them, in the capacitor. So when a capacitor is charged by connecting it to a battery, charges of equal magnitude but opposite sign reside on conductors. Since the plates are conductors, they are equipotential surfaces. So they are equipotential surfaces. Okay. So the parallel plate capacitor is one of the very common configurations. So when you saw that when you charge them, uh, when you charge the capacitor, here's where the charges reside. Okay, so in an ideal capacitor, okay, so ideal capacitor is the area is much larger than the separation between them. See the charge, all the electrons are on this surface, and all the positive charges are on this surface, on the inside face. And why did the charges distribute like that? To make the electric field inside the metal zero. Okay? And then there's an electric field between the plates, and ideally the field outside is zero. Okay? So when you charge the capacitor, you can think of that as energy stored in the electric field. If there is no charge, there's no electric field. Okay? So the energy stored can be thought of as two ways. Anytime you create an electric field, you have stored energy in the electric field. Okay? So we'll give you an expression for how much energy is stored in the electric field per unit volume in a little bit. Okay? When the electric field goes to zero, you've used up that energy. Okay? So similarly, we'll think of whenever you create magnetic fields, you store energy in magnetic fields. Okay? All right. So capacitance is defined as how much charge it can hold, the device can hold per unit volt. Okay? The larger the capacitance, the more charge it can hold per volt. Okay? The units for capacitances are called farads, after Mr. Farad. Okay? 1 farad is a very large capacitor, and back 30, 40 years ago that it used to be very expensive. But now you can buy 5,000 farad capacitors. Even you and I can, even David can buy one. So you can go to Amazon and find it. Okay? So most of the capacitors that we use, okay, your chips have several capacitors, hundreds of capacitors. Those guys use microfarads or picofarads. A picofarad is a trillionth of a farad, 10 to the minus 12. Micro is 10 to the minus 6. Okay, here are the electrical symbols. So there's a symbol for a capacitor. This is the symbol for a wire. That's a resistor. A resistor, like the name suggests, provides friction. It turns electrical current into heat. Okay, that's what's in your toaster. That's what's in your water heater. Okay. And those are materials that convert electricity into heat efficiently. This is an inductor that stores energy in the form of magnetic fields. And what this guy doesn't like is he doesn't like changing currents. So if you change currents, he doesn't like it. So the faster you change current, the more he dislikes it. So in an AC circuit, this guy provides resistance. Okay. This is just a switch. This is a galvanometer, a voltmeter, ammeter. This guy measures current. This guy also measures current. This guy's a battery. This is an AC source. Okay. All right. So here's a circuit. This is a very versatile circuit. So when you close the switch, current flows from and charges the capacitor. And once the capacitor is charged, you can open the switch, and now you have a charged capacitor, and you can use this energy whenever you want. Okay? And when you're ready to take a picture, you click your camera. At that same time, that switch closes, and this capacitor is discharged. And then you open the switch, and the camera automatically closes the switch, and that blinking orange light is telling you that the capacitor is being charged. And once that light goes green, then that means that capacitor is charged, this switch has been opened, you're ready to take another flash picture. Yeah. So this is the circuit in your flash camera. This is also the circuit in a defibrillator. The battery charges the capacitor. Once the capacitor is charged, you can jump start somebody's heart. Yep. And so on. All right. So, yes, so the so the most commonly, so what is it that you need for a capacitor? How do you make a capacitor? Two pieces of metal. Okay. This is a capacitor, except that what is the value of this capacitor? I don't know, I have to measure it. For this capacitor, I can give you a formula for the capacitance in terms of the geometry. Okay, so for a parallel plate capacitor. And again, right, they have to be on top of each other. For instance, if this guy is, so the two sheets of paper have to be opposite each other. Okay? If they're like this, transposed, then I can't give you a formula. Okay? So for this configuration, the capacitance is epsilon naught is the permittivity of free space. It's a constant. Area of the plates divided by the distance between the plates. Okay? So if you want to increase this value of the capacitance, you can increase the area of the capacitor or decrease the distance between the plates. Okay? And as you decrease the distance between the plate, the electric field strength increases for a given charge, and then eventually they'll discharge. Okay? So ultra capacitors, large capacitors are made by increasing the area of the plates, and I will show you how to increase the area of the plates, effectively increase the area of the plates. So here's a cylindrical capacitor. Coaxial cables have capacitances associated with them. So here's the inner metal and here's the outer metal. The capacitance is the length of this cable times 2 times the Coulomb constant log of the inner radius of the outer conductor. Inner radius of the outer conductor divided by the outer radius of the inner conductor. Here is two concentric metal spheres, okay? And the capacitance for this is the inner metal radius times the outer radius divided by K B minus A. And here is one case you can think of making a capacitor with a single conductor. All you do is make this go to infinity, and then you don't have this guy anymore. And in the limit b going to infinity, this expression reduces to that. So the capacitance of a single a spherical metal conductor is the radius of that sphere divided by Ke, the Coulomb's constant. Okay, and you've seen those capacitors. So these guys, Van de Graaff generators, this metal sphere that is being charged. Okay, and have you guys ever seen stuff like that? Okay. Yeah. And the way it charges is the following. It charges by friction, just like when you walk across a carpeted floor wearing rubber soles. Okay, friction charges it. Okay, so here's how the thing is charged. Okay, this is a rubber belt, and as this rubber belt goes by, here's a metal brush that is scraping off electrons, and the electrons are going there. So now this rubber belt has become positively charged. And here's another metal brush that is stealing electrons from this metal sphere and putting it back there. And then those electrons are transferred over here. So eventually this thing will become positive. Charge builds up. So that's how Van de Graaff generators are charged. That's triboelectric charging. All right, So so now how do we combine capacitors? Okay, so you can combine, here's a parallel combination, see. So parallel combination is these plates are both connected to this voltage. So when you have parallel combination like this, okay, if this is a 10-volt battery, this charges to 10 volts and this charges to 10 volts as well. Okay. And now the total energy stored is the energy stored in this plus the energy stored in that. Okay. So when you want to store a lot of energy and you can't store energy in one capacitor, you just use several capacitors and connect them in parallel. Okay. And that's what they do in fusion reactions. They'll have a bank of parallel capacitors, and then they'll fire all these capacitors and shoot lasers. And the lasers are shot at a pellet, okay, where you hope to have fusion reaction. Okay. So here's a parallel combination. And when you have parallel combination, the equivalent capacitance is just the sum of the capacitors. When you have parallel capacitors, the voltage is the same. Okay, when parallel capacitors are connected in parallel, voltage across each capacitor is the same. Here is a series combination. This is a series combination. Okay, let's make sure we understand this. In a series combination, okay, electrons will flow from here to there. So let's say 10 electrons flow from here to there. What happens next? These guys will repel 10 electrons, and 10 electrons will go from here to there. These guys will repel 10 electrons, they'll go from here to there. Those 10 electrons will go over here. So when you connect capacitors in series, the charge on each one of them is the same. Okay? So the charge on each one of them is the same. And if this is a 20-volt battery, the voltage across this plus voltage across this plus voltage across this will be 20 volts. Okay? So that's it. And the equivalent capacitance is the inverse sums. And so look at this expression. See, this guy is equal to this plus this plus this. So this guy is greater than any of those. So that means the equivalent capacitance is smaller than any of those. So when you connect capacitors in series, the equivalent capacitance is smaller than the smallest one. Okay? So when you want a bigger capacitor than what you have, then you connect them in parallel. And if you want something smaller than what you have, then you connect what you have in series. And hopefully you get to the value you want. Okay. So in a parallel connection, the voltages are the same, and in a series connection, the charges are the same. Right, here's a mess of capacitors. Oftentimes what we'll need to do is calculate this equivalent value of this mess of capacitors. Okay, so the procedure is the following. If you have a parallel combination, combine the two, then combine the series combination. Here's a parallel combination, combine the two, then combine this series. So this is equal to that. This is equal to this. Now these guys are in series. Combine those two. Now these guys are in parallel. Okay. So you go step by step until you reduce it to a single capacitance. Okay, when you charge capacitors, like we said, you're storing energy. Again, you can think of them as a stretch spring. The amount of energy stored is 1/2 times C, the capacitance times the voltage to which you've charged squared. Okay. So that's the energy stored. So you can think of this as the spring constant, and that's how much the spring is stretched in the voltage. Yeah. So like 1/2 kx squared. So here's a charged capacitor. And if the capacitor was not charged, the electric field is 0. And when the capacitor is charged, there's an electric field in between. Okay, so ideally all this field is 0. All the field is right there in between the capacitor plates. Okay, so you can think of the energy stored in the capacitor as the energy stored in the electric field. And that's what this formula gives you. So the energy stored in the capacitor is 1/2 CV square. For the parallel plate capacitor, C is epsilon naught A D divided by D. The voltage across the capacitor is E, the electric field times the distance between the plates. Okay, and so you can square that. And you can rearrange this and write this as A times D. A times D is the volume in between the capacitor plates. That's the volume between the capacitor plates. And here's an expression that depends only on the electric field and a constant. So you can think of this as the volume times the energy per unit volume. So this is the energy density. Okay. So whenever you create an electric field, the energy density in the field is given by 1/2 epsilon naught E squared. Okay. So that's how you want to think about it from now on. Anytime you've created electrical magnetic fields, you've stored energy in the fields. Okay. And of course, you can use that field in stuff. Okay. And that makes sense. You're communicating electromagnetically. That electric field carries energy, and that when that electric field hits your antenna, it sets up a current in your antenna. Okay? So it's deposited energy. It's like if you have a boat anchored in a lake, you drop a rock somewhere else, that wave is carrying energy, and can lift your boat up and down. So, okay, here's one of the problems you face. You charge a capacitor, and if there was nothing holding them apart, the plates would come together and all your money will go down the drain. So what do? You just stuff it with an insulator, and that's a dielectric. Okay? So a dielectric is a non-conducting material, such as rubber, glass, mineral oil, etc. With the dielectric present, capacitance increases by a factor called the dielectric constant. So different materials have different dielectric constant. So now the capacitance will become the dielectric constant times the capacitance without the dielectric. Okay? So it increases by that factor. So there are times when you want to increase you want it for several reasons. So look at this. Teflon, the dielectric constant is 2. Pyrex glass, it's about 6. Paper, about 4. Strontium titanate, the dielectric constant is 233. Water, 80. Anyway. All right, so with the dielectric constant, you increase the capacitance. Okay, what happens is, so here's what happens. With the dielectric present, so here are the plates. Dielectrics are okay. So here's a capacitor, interwoven metal plates with silicone oil, or some kind of oil. Okay. So high voltage capacitors consist of many interwoven metallic plates immersed in silicone oil. So I don't know if they still do this, but here's some of the older keyboards were made of capacitors. Okay, so here's the deal. So they connect each of the keys, each of these to 5 volts. And when you press down on this key, here's how the computer knows that which key you press down. When you press down on this key, the distance between these guys decreases. Capacitance, which is Q over V, charge over the voltage. The voltage connected is 5 volts, is epsilon naught A over D. When D decreases, capacitance increases. So for the same voltage, charge flows in, more charge flows in. So as soon as you press down the key, more charge flows in onto that plate. And that's how the computer knows which key you pressed. Okay, so that's one way of telling which key was pressed in a computer. Yeah, so here's a Z machine. These are fusion reactors. Okay. The Z machine used a bank of capacitors connected in parallel. So when you want to store more energy, you take a bunch of capacitors, connect them in parallel. 1,000,000 joules of energy was stored. 1,000,000 joules is the same amount of energy as a 100 kg person standing a kilometer high. So you guys see those Embry-Riddle planes flying on the beach? So if I was standing that high, that's how much energy I would have, 1,000,000 joules. The energy is discharged through a target about 1 cc. One cc is about this much. In a few nanoseconds. So you discharge all of that energy in a few nanoseconds. Okay, remember for a flash camera, how much energy was discharged? 20 joules. So this is almost 100,000 times more energy. In a flash camera, you discharged it in a millisecond. Here you're doing it so almost 1,000,000 times the energy, and you're discharging it in 1,000,000th of the time. Okay, and it heats that sample to a temperature of 2 billion degree Kelvin. And in that sample, the protons, so if this is hydrogen, those protons will be going so fast that they'll come close enough for strong force to take over, and they'll combine into helium nuclei. Yeah. See, protons want to repel each other, so if you want to bring them real close, they have to be traveling real fast. Yep. Here's the interesting part. In the center of the sun, the temperature is 15 million degree Kelvin. Look at this. In this little pellet, you're creating a temperature of 2 billion degree Kelvin. A 100 times greater than the center of the sun. Why is that? Okay, the pellet has, it doesn't have that many hydrogen. In the center of the sun, okay, here's the velocity distribution. Okay, so at 15 million degrees Kelvin, most of them are going slow, but there's enough protons in the tail that are going fast enough to combine. Okay, in your small pellet, you want to make as many go fast enough so you get enough useful energy. Okay, so that's why you have to. For that nanosecond, when you discharge that 1,000,000 joules through the thing, and what you're doing is, so here's your pellet, Here's your pellet, and what you're doing is you're firing several lasers at the same time. Yep. And hitting that pellet. And look at this number. Okay. So for that nanosecond, the power output of the Z machine, this by the way is in New Mexico, Sandia National Lab. Yeah, you used to run next to it. What's that?
There's a lot of nice stuff there.
Yep. The power of the Z machine is about 100 times the combined power output of all the power plants on Earth. Those are big boy toys. Lawrence Livermore has something similar. Nuclear fusion reactors is powered by 192 power conditioning modules, each containing 20 30 microfarad capacitors. It's charged to 24 kilovolts. Again. They take 90 seconds to charge and 400 microseconds to discharge. Okay, so for a parallel plate capacitor, the capacitance is given by area of the plates divided by the distance between the plates. Okay. Now, if you want to increase the value of the capacitance, one of the best ways to do is to effectively increase the area of the plates. Okay, and so supercapacitors and ultracapacitors are made by effectively doing that. And the way they do that is, this is supercharged carbon, okay, activated charcoal, and that's just fine charcoal, fine carbon particles. And the surface area of those particles effectively adds area to the plate. Okay. So now when you charge the capacitor, you're charging the surface of these carbon particles. 2 layers of activated charcoal are given opposite charges and separated by an insulating material. Okay. So that's the dielectric, and the carbon particles are acting like the surface. This produces a capacitor with capacitance millions of times larger than the ordinary capacitors. So 5,000 farad capacitors are commercially available. So, but you can only charge these capacitors to 2 to 3 volts, and energies of 10,000 joules can be stored in these capacitors. So, remember, in your flash camera, you only stored about 10 joules, so 1,000 times more energy can be stored. So, in big cities, you have these. Okay, so if you run your city buses on gas, of course you put carbon dioxide in the atmosphere, create smog and stuff like that, and buses don't burn their fuel completely, so you have these smoke particles and all that. So here, ultra capacitor, these guys run on capacitances, and the idea is the following, and this is useful in cities. You come to a bus stop, by the time the passengers get in, the bus is charged, the capacitor is charged. You go to the next station, and so you can run all day long. Okay.